Hey guys, this is the second video in Chapter 4, Net Ionic Equations. Now, net ionic equations may seem like a very small part of Chapter 4, but it's a really big idea that students miss every single semester. So I'm going to break this down for you one step at a time. So going back to our previous video, we had this slide where we talked about double replacement reactions. And we talked about how barium sulfate was a solid. Now, why was barium sulfate a solid? Well, it was a solid because it is a weak electrolyte. What does that mean? Well, electrolytic solutions are based on how much a solute dissociates. Basically, if we dissolve something in water or in our solution, and it splits apart completely, like we see with sodium and chloride there, it splits apart completely or breaks up completely. We call that dissociation. You can think of it as disassociating. They're not associating with each other anymore, right? If it only does that a very slight amount, it's called a weak electrolyte. And if it doesn't do it at all, it's called a non-electrolyte. So we see three examples of those on the slide there. So how do we know? So we said barium sulfate was a weak electrolyte, and that's why it didn't break apart. But how do we know that it's a weak electrolyte? Well, we only have a few options for strong electrolytes. Here are all of our options for strong electrolytes. We have strong acids, which we only have 7 of them, which are listed there in the top left. We have strong bases. Okay, so we have these strong acids. Here, hydrochloric, hydrobromic, most of the ones we use in the lab, you can read those, 7. Strong bases, group 1 metal hydroxides, so all of the group 1 metals there. And heavy group 2 metal hydroxides, calcium, strontium, and barium hydroxide. So strong acids, strong bases, or soluble ionic compounds. Okay, so we have those 3 options, strong acids, strong bases, and soluble ionic compounds. Now, in order to determine if it's a soluble ionic compound or not, what we have to do is look at these solubility rules. Now, unfortunately, you are going to have to memorize the solubility rules. However, there are 6 ions that, if they're present in the ionic compound, then it will be soluble. Those are nitrate, acetate, chlorate, perchlorate, and then the positive ions, lithium, sodium, potassium, and ammonium. If those are present in the ionic compound, the compound is said to be soluble, or the ionic compound is said to be soluble. You can see some of the other ones kind of down here. Okay, you have a list of these in your lab book in experiment 4. It's really nice. I like that solubility table quite a bit. But you can see for the halogens, they're mostly soluble, except for whenever they have silver, mercury, or lead as a component of that compound. Sulfates, also mostly soluble, except for strontium, calcium, barium, lead, and mercury. Fluorine has much the same as far as the different insoluble compounds, except for magnesium, sulfur, and silver is added in there. These compounds down here are usually not soluble. And so take a look at those solubility rules. You're going to have to know them, and unfortunately I don't have anything better to help you with it other than for a lot of the exceptions, strontium, calcium, and barium do show up. You are going to have to work with those and memorize those in order to get proficient with them, but it's not as bad as it seems. Now on to net ionic compounds. What are we talking about when we say net ionic compounds? Well, net ionic compounds represent a better picture of what's going on in a solution. And so what we're looking at and what we do is we dissociate strong electrolytes. Remember these guys, strong acids, strong bases, soluble ionic compounds. Weak electrolytes and non-electrolytes we leave undissociated, so we get a very good picture of what's actually going on in solution. So here's an example of our of our original reaction of this reaction up here. We have sodium sulfate and barium chloride. So let's take a look at what it would look like if we did the total and net ionic equation. So what we do is we have to identify what these are. Well, these are all ionic compounds, right? All of these guys are ionic compounds. And so what we use is the solubility rules to determine if they're soluble or not. Soluble ionic compounds are strong electrolytes. Non-soluble ionic compounds are not strong electrolytes. They're weak electrolytes. So sodium, always soluble no matter what. So this guy, we're going to put AQ to denote that it's soluble. Barium chloride, also soluble. Sodium chloride, soluble. Barium sulfate is a solid. Sodium always has to be soluble, so we know those two are. If we go back to chloride, they're usually soluble right here. They're usually soluble unless we have silver, mercury, and lead, which we don't with barium, so that's good. So now what we're going to do is we're going to break each of these up into its cations and anions, into its actual ionic species, except for our solid. That's going to stay together. So we do that, and here's what we get. And there's a couple of things that I want to point out. One is the fact that sodium, we had two sodiums, but when it breaks apart, it becomes two individual sodium atoms. So this 2 gets moved to the front because it's two individual sodium ions. And the same thing here. So we've got 2 sodiums and 2 chlorines. Now, this is the total ionic equation. Now, what do we have to do to get the net ionic equation? Well, what we do is we look and see what's the same on both sides. Here we have sodium and we have chloride. And so we remove those from the equation, and whatever's left over is my net ionic equation, which will look like this. Barium plus sulfate makes barium sulfate. And a lot of the net ionic equations are fairly simple like that. Okay, so again, split apart strong electrolytes, left weak electrolytes together, canceled out whatever the same or whatever species are the same on both sides. These are called spectator ions because they don't do anything. And then rewrite whatever's left over as my net ionic equation. Let's take a look at another example. Okay, so here we have sodium nitrate and potassium chloride. I know compounds of sodium are always soluble. I know compounds of potassium are always soluble. So this one's soluble, this one's soluble. So we're going to split up. These are all ionic compounds. So we're going to dissociate all of them because they're all soluble ionic compounds. And it's going to look like this. Now let's cancel out our spectator ions. Well, we have a sodium on this side. We have a sodium on this side. There's a chloride, there's a chloride, there's a nitrate, there's a nitrate, there's a potassium, there's a potassium. So this is no reaction. No reaction. Why is it no reaction? Well, if we look here, we've got a beaker, and don't laugh at my drawing here. We've got a bottle, a beaker, whatever. Looks more like a little vase, but that's fine. And here we have another beaker. That's terrible. But here we've got potassium ions and chloride ions, and here we have sodium ions and nitrate ions. So we're going to pour these guys together in a big beaker. And so we have potassium ions and nitrate ions and sodium ions and chloride ions. There is no difference between these species and these species, right? In order for a chemical equation to occur, and in order for a reaction to happen, we have to form a new compound. And because all of these are soluble, it's just ions in solution. And just because we mix them together, nothing new happens because there is no change. We don't make anything new. There's still ions floating around in solution. They just happen to be in the same container at this point. So it's important to realize that if you don't have anything that's changing, you have no reaction, even though we can write one on what's called a molecular equation up here. One more go, and then we'll be done. Here we have acetic acid and ammonium hydroxide. Now going through again, we have to kind of decide what kind of compounds these are. This is an acid, right? And this guy is a base. This is an ionic compound. And this is a covalent compound. So here we've got all different types of compound, all different types of stuff here. If we go back to our thing here, we see that strong acids and strong bases are strong electrolytes, but ammonium hydroxide is not on this list, and acetic acid is not on this list. So even though they're soluble, sure, I mean they're soluble compounds, it's an acid and a base. Don't get them confused with ionic compounds, where we have ammonium as always soluble and always. So what we're going to do is leave these guys together. Now this is an ionic compound, and remember, ionic compounds containing ammonium are always soluble and therefore strong electrolytes. So this guy's going to split apart. And then this is a covalent compound. Remember, we only have 3 options for strong electrolytes: strong acids, strong bases, and strong and soluble ionic compounds. So this is just a liquid, and we're going to keep that guy together too. So whenever we break this guy apart, there's only one thing that's going to dissociate. That is my ammonium and acetate. These stay together because they're not strong acids and bases. This is a weak acid, and this is a weak base. So keep them together. And I know you're freaking out saying, but ammonium, it's right there, it's right there. You know, isn't that always soluble? Yes, it's soluble, but it doesn't dissociate because it's a base. We're considering it a base. And remember, for bases, only group 1 metals, calcium, strontium, barium hydroxide. Those are the strong bases. Everything else is a weak base that's going to stay together. And so if we cancel out our spectator ions, we don't have any spectator ions, and so our net ionic equation is going to look just like that. It's going to look the exact same because we don't have any spectator ions to cancel out. And I actually forgot my AQ for ammonium here. Be a point off. So so just a couple things to point out. We always put AQs for ions and the soluble stuff. Liquid for water because that's our solvent. And I think that's about it with there. We have a big sign that I cannot stress enough. Weak acids and bases do not dissociate completely. Therefore, in a net ionic equation, we leave them together as a molecule because that is the predominant species in the bottle or in the beaker or whatever, in the reaction. You know, acetic acid only splits up about 1% of the time. Only 1% of the molecules that are in solution dissociate into ions. The rest of them stay as molecules, and so the best, I guess, representation of what's going on in the beaker is leaving it as a molecule because 99% of it is molecules. It stays as a molecule. So that's the best way to represent it. Do not break apart weak acids and weak bases with net ionic compounds. Hopefully that catches most of you, and so you don't do that on the exam, because that is always heartbreaking to count off so many points whenever it's such a simple idea. Weak acids and weak bases. There's not a lot of memorization for weak acids and weak bases. You have 7 acids, group 1 metals, calcium, strontium, barium for bases. If it's an acid and base and not those, leave it together for the net ionic equations. Anyway, I'll see you next time whenever we'll talk about molarity.